Hi, Robin here. We're going to look at big O notation and we're going to be looking at the complexity of algorithms. Okay, so this is suitable for particularly the OCR A-Level, but again will be appropriate for AQA and other exam boards if necessary. Okay, so what we've got here is the concept of complexity, and really, ultimately, when you think about it, all we're trying to do is write an algorithm in the most efficient way possible. And what big O notation does is it enables us to analyse the algorithm and actually work out how efficient it actually is. Efficiency is one of these things where we can think of that from the amount of memory that's required to run the algorithm, the speed that the algorithm will actually complete, but also if you think about it, it's the need of hardware that that algorithm creates. So if you're going to use up a lot of memory, then you're obviously going to need to purchase more memory, and therefore that comes at a financial cost. But also, if you're going to need more memory and more steps within a process to complete it, you therefore may need better processing capabilities, and therefore again increases cost, but also increases things like power consumption, etc. So within your scenario, whatever situation you were in, you should always consider this, and therefore ultimately can save yourself a bit of money and run the correct hardware for the situation you're in. Okay, so when we're looking at an algorithm, we want to consider the 5 fundamental operators, and these are the basic principles within any algorithm that will cause some sort of computational step to need to be required, and therefore will come at some form of cost. So you can see in here arithmetic, comparison, assignment, memory lookup, and returning value. So whenever any one of those things happens, we should then factor in the cost of doing so. So for example, I've just got a simple algorithm here, and what you can see is we've got some memory lookup where we're looking for the values in those particular variables. We've got a comparison, so the I being compared to 1. We've got some arithmetic taking place of the total plus I. We've got the assignment of the 0 into the variable of total, and again the total plus I going into the value of total. And we've also got a returning value. The thing to notice with this algorithm, what's important about it, is everything within that red box is within a loop. And that's really important, because what that means then is every time that loop happens, those same fundamental operators will be carried out again and again and again. And obviously what that means therefore is that we're getting multiplications of it. So if we think about this particular algorithm has a calculation of the, first of all, the assignment, then the 6 fundamental operators that are within the loop. That is controlled by the size of the for loop. So you can see the for loop will loop until it reaches the given number, so whatever number has been entered, and therefore then also has a returning value at the end that's added to that. So in other words, if given number is 1, it will be the 1 of a total of assignment plus the 6 within the loop plus the final 1 of the return. If given number is 2, well then we've got the 1 of the assignment of total, we've then got 6 plus 6, finally we then have the 1 of return. So you can see that the given number value actually has a big impact on the efficiency of this particular algorithm and how costly it would be. So in other words, what we can then consider is the cost of that particular function is its order of growth. In other words, as given number increases, so does the cost of that particular algorithm. You're required to understand and know about these 6 different big O notations, so constant time, linear time, polynomial, exponential, logarithmic, and factorial. So I just want to go through those now, and we can sort of see kind of the impact of them. So what we have here is quite a simple graph, but you can see each of those different complexities have been shown on that. What I would suggest is that once we've talked through them, you actually come back to this and you can sort of see and compare the different algorithms with it, just so you get a bit of a better understanding and can sort of see again the cost. But if you imagine it, if it's green, that's really good. If it's red, that's really bad. Okay, so it gives us a sort of, again, an idea, a visual way of seeing and imagining how bad or good a scenario is. If we consider constant time, what we've got here is any situation that just repeats and it's the same regardless of what happens. So in other words, to remove the head of a queue or the top of a stack will do so. It'll remain constant all the time, as you can see here. So as the data is removed, that one data happens each time, and we're not bothered about the size of the queue or the size of the stack in this instance, just purely because all we're considering is what computational steps would be required to dequeue. In other words, we're the cost of moving the front pointer across one to cope with that, or again moving our top pointer within our stack down and popping our data from that stack. And therefore that's going to be consistent every single time. A situation like a linear search, and you can see the graph right there, this is where any action is in proportion with the size of data, and a linear search is a very good example of that, as you can see here. So if I'm searching for the number 1, if I've got the data of 4, 3, 2, 1, in other words, I would look at 4 first of all, then I would need to look at 3, then I would need to look at 2, and then I would find the data item I'm searching for, in other words, 4 searches, whereas obviously as the data set grows, so does the number of comparisons that are then required to find that particular item. Our polynomial time is where we're increasing in relation to the size of the data, but it's also one of these things where this is quite costly now. You can see that the curve is increasing, particularly as the data gets larger, the data set gets larger. And a bubble sort is a very good example of this. As you can see here, what we've got is we've got 6 pieces of data in our original list, but because they're in the worst case scenario, in other words, they're completely back to front, it actually takes the 1, 2, 3, 4, 5 plus the check, so in other words 6 goes through to actually check that the bubble sort is complete. In other words, we've got 6 passes for 6 pieces of data. So in other words, we've got 6 times 6, which is where our big O notation comes from, being it squared. Moving on then, we've got a logarithmic. A logarithmic, really we consider good. In other words, because as you can see, as the data set increases, this levels out. So whereas at first you could argue that that angle of the graph would be like red, once it's increasing data size, it's gone green. And the reason for that is that particularly divide and conquer algorithms reduce very, very quickly as data sets get bigger and bigger and bigger. So for a simple example, if you've got 32 million pieces of data, in the very first step, you'll be able to reduce that down to 16 million. Then in the second, you'll be able to reduce that down to 8 million, then the third, 4 million, fifth, 2 million. So in other words, you're losing like 30 million bits of data in only 5 steps, which is incredible, isn't it? It's very, very efficient when you think about it, rather than having to step through like a linear search would through 32 million data items to find that. And we can see that here with the binary search, that we start off with our 8 items. Because we've used the middle one, we can actually discard 5 of them in this case, and therefore we've now got 3. And then finally, if we're searching for one, we will find it in as few as 3 steps, which is very, very efficient. Again, in comparison, if we were doing a linear search in the worst case scenario and we were looking for 8, for example, that would take us the full 8 steps, wouldn't it? So it'd be much, much more costly. A merge sort is n log n, and I think it's worth considering why, just so that you get this further deepened understanding of your sorting algorithms. So this part of it here is exactly the same as the binary search, and really that makes sense because what we're doing at the start is halving, isn't it, each time? In other words, we're creating these divisions just like we do in a binary search. So you can argue that everything in this part of the algorithm is just a binary search, or a version of it in a way, where we're dividing it and dividing and dividing. So in other words, the same benefit we had before, we're getting now. The only reason that we've got this additional n at the start of the complexity is because of the requirement to compare. And what we've got here is we've got a comparison that's having to happen. And again, we end up having to do sort of as many comparisons as a minimum as there are data items to establish that. Because even if this row above already read 1, 2, 3, 4, 5, 6, 7, 8, we would still need to compare across the two lists to do so. So again, the n is determined by the size of the data set in that regard. So again, just 2 items of data in it would only be compared twice, whereas 8 obviously more likely to need to at least be required to compare 8 times. We also have exponential time. So when we think of exponential time, you can see that it is incredibly costly. If you remember the coloured graph that I showed you, that would be very much in the red. Very simple example of exponential would be a virus. So when we think of a virus, we can think of this from a human point of view, but this is also true for a computer virus when it's duplicating within your computer and therefore causing sort of memory hold-ups within the computer and therefore causing it to stop working effectively, blocking and stopping it from, well, okay, our next one then, if we think about exponential time, you can see that the graph is incredibly steep. In other words, it would be red, and you can sort of you can see that it's really quite a bad one, and in certainly in speed. So in other words, as the data size gets bigger and bigger, it gets worse and worse and worse, more and more costly. And the spread of a virus is exactly this. You can think of this from a real world spread of a virus and how quickly the pandemic spread, for example, across the entire world because of the speed of the exponential growth of that virus, the coronavirus. But if you think of this also within a computer, that is also true of a computer virus, particularly those that are duplicating, because as each one duplicates, it'll double up, as you can see here. So in other words, we have the one computer virus, it then doubles, and then each in turn of those doubles, and so on. And you can see how quickly that's going to generate more and more files within your computer and therefore sort of starve your computer of memory locations and therefore obviously cause ultimately the computer to stop working. Our next one then is factorial time. Factorial time is basically the worst. You can see it's so steep there, isn't it, in that graph. And that this is because we've got scenarios where we consider them intractable. In other words, we can't improve them. An example of this is a travelling salesman or salesperson role. And all we've got here is a scenario where we've got 3 destinations, so Manchester, London and Edinburgh. And in other words, the salesperson has to choose one of them to go to first. We're ignoring things like geography and mileage and all that sort of stuff. We're not talking about that. We're just talking about the options. So there's 3 options to start off with. Once you've chosen, for example, Manchester first, they've got 2 other options to go to, London or Edinburgh. So then you've got a choice of 2. Once you've chosen again, so you choose London next, you then still have a remaining choice to make, which is then Edinburgh. So in other words, we've got this factorial happening of the 3 times the 2 times the 1 in the decision process and the options that you can then take. And we call this intractable because you can't actually improve it. Obviously, in reality, we could improve this by factoring in geography and mileage and all those other things. But when we think of factorial problems, this is a situation whenever you can't improve it by the situation that it is. And really, we want to avoid these as much as we can. Hence why, like I've suggested with this one, we would want to factor in other elements, such as mileage, to try and avoid that issue. When we're talking about complexity, something we should be very mindful of is the best, average and worst case scenarios. And often a worst case scenario would be the reverse situation. We've talked about this earlier on, where the example of the bubbles sort that I gave you, very much a worst case scenario. And generally speaking, if you think about it, the best case is literally when if you're doing a search algorithm, you literally find it in the first step. And obviously the average will be the kind of the most usual. So again, we want to think about the situation the data starts in to decide whether or not that's going to influence the choice of sorting algorithm we use or search algorithm or whatever it might be. The other factor that we need to consider is what we call space complexity. So far I've only really talked about time complexity. With space complexity, we're talking about how much memory is being used by the process. So we've seen quite a lot of sorting algorithms, and most of those will use what we call in-place sorting. In other words, the data remains in the same memory location, it's just is moved around within that sort of environment that it's in. So what I mean by that is if you think of an array stores data contiguously, the data is together, and therefore all the sorting happens within that preset area of memory where that data was stored as an array. So it doesn't require, therefore, other memory needs. If we have out of place sorting, that's where we're taking up other storage needs as we carry out the algorithm, as we carry out the process. And obviously that becomes much more costly. An example of that is a merge sort. As it's creating all these new lists, it can therefore take up more and more space. It's why we consider a quick sort to be more efficient than a merge sort, because even though they've got the same time complexities, they're both n log n, we would say that quicksort is generally quicker and better to use because it uses less space complexity. It doesn't require additional memory storage as it's being carried out. When we're thinking of other data structures, for example, we can sort of compare an array with a linked list. If you think about a linked list requires extra data to store the different pointers between the different stages of the linked list, whereas an array, as I already said, is contiguous. You don't need to do that. So whereas an array you step through, the linked list you need to move through those various paths. That's obviously going to impact on the amount of storage you need, because if you're going to need more data for a linked list, but also it's going to impact on the process in the way that you sort that particular data set in. If we compare it to something like a hash table by its very nature should be constant, and therefore, though it's really great from a searching point of view, finding different pieces of data, etc., it's going to be very expensive from a space complexity point of view. So again, when you then have your data stored around your different areas of memory, it's harder then to manipulate and move, and will therefore kind of cause you additional problems. Here again, we think about a multi-dimensional array. Because the data is stored in now a more complex method, rather than just being able to step through the data like we could very easily with an array, a simple one-dimensional array, we've now got to factor in this additional moving through each layer, moving through each column, moving through each row. And obviously that, again, the more layers and rows and columns you've got, the more loops that are happening, the more cost is involved in both time complexity and the space in memory to store that. Okay, finally, to summarise then, it's really essential that you do learn these, that you're really familiar with each of the sorting algorithms, how they compare with each other, which is the better, which is the worst. So I often say to students, if you think of this like a race, you can imagine the quick sort, the fastest, it's a logarithmic, it's sort of already finished the race, it's celebrating, it's having a great time. The merge sort, again, is a logarithmic algorithm, so it's again very quick, but because of its space complexity, it therefore is slightly less efficient than the quick sort, and therefore we'd consider it the slightly slower, the second best choice, if you like. Then we can have the insertion and bubble sort, both with similar time complexities, both not particularly brilliant, particularly as data gets bigger and bigger, and you kind of imagine them huffing and puffing along as they bring up the rear. We would probably suggest that the insertion sort would pip it at the post and get third place, the bubble sort would come last. And then with our space complexity, you can see again that with quicksort being logarithmic, whereas the merge sort requires that additional storage because of each of its data set values, we would again consider that more efficient and therefore the better option. However, both insertion and bubble sort are highly efficient, again, from a space complexity point of view, with being sort of the O1 big O notation. Okay, well, I just wanted to say thank you for watching. I really hope you found it useful and really hope you've learned something. Please do like and subscribe, and I'll hopefully see you again. Thanks a lot. Bye.